everyone, Charming Joyce Bolo here. So for today's discussion, we are going to learn something new. But when it comes to business statistics, the principles of statistical identification are those that will enable us to utilize the appropriate techniques. We often refer to things like independent trials and decision theory. I'm not sure whether this topic that is new to us, but we, the Group 4, will enable you to comprehend what it is through presentation, problem-solving activities, and examples, so that you can have a better understanding of it and actually understand more about it. Without further ado, let's go to our conceptual framework, which is the flowcharts of our discussion for today's video. So we have first the independent trials and concept to be reported by Ms. Arobo, and we have problem and solution by Ms. Donan, and of course examples with solution by Ms. Jelen. And of course, we have decision theory, introduction, and concept to be reported by Ms. Balid. And of course, the problem and solution by Ms. Alonde. And of course, the examples and solution by Ms. Dimicelio. And for our learning objectives, we have first identified the basics of independent trials and decision theory to determine the potential outcomes for a given situation. The second one, describe the independent trial concept and decision theory concepts. And of course, the third one is to make the best decision by comparing all the possible alternatives. And the last one is to precisely figure out the problem and to provide examples with solution.
Good day everyone, my name is Kathleen Arubo and I will be giving you the introduction of independent trials so that when Ms. Donan and Ms. Dylan will have their examples and problems, you won't be confused anymore and you already have background of what is an independent trial. So what comes to your mind when you hear independent? Like, we can immediately think that it is about a strong, independent person that has the ability to stand alone without affecting others, or it's just you and no one else, right? Then the term trial, like trial card. Well, let us start the discussion so that we will know what is independent trial in statistics. So in my discussion, the term independent trials is just synonyms to independent events. Don't be confused when you see or when you hear event instead of trial. So to start my discussion, I will first give you definitions. Independent trials, according to glossary, independent if the occurrence of one event does not affect the chances of the occurrence of another event. In mathematics, independent events do not affect one another and do not increase or decrease the probability of another event happening. So with the two definitions given, it is clear that independent trials or event means that if probability of one thing happen isn't going to affect the next. Every time we hear the word independent, we all know that its opposite is dependent, which actually it is independent and dependent events. So let us have a quick differentiation between dependent and independent events to further understand what is an independent event. So dependent event. When two events are dependent, the occurrence of one event influences the probability of another event. Here, sampling be done without replacement. So, what is without replacement and why it is dependent? Without replacement, each member of population may be chosen only once. If sampling is done without replacement, the probabilities of the second peak are affected by the first event because you can only choose once. While the independent event, when two events are independent, one event does not influence the probability of another event. Sampling may be done with replacement. So with replacement points out that each member of population is replaced after it is peaked. Then that member has the possibility of chosen more than once. If the sampling is done with replacement, then we can immediately consider that the trial or event is independent. Why? Because we keep on replacing what was picked in the choices to keep the original amount intact. In that way, second event to follow will not be affected.
You can use the equation below to figure out probability for independent events. Here, the probability that both events A and B occur is equals to the product of the probability of event A and probability of event B. Events A and B are independent if the equation holds true. You can use the equation to check if the events are independent. Multiply the probabilities of the two events together to see if they equal to the probability of them both happening together. So, with that formula, the next reporter, Miss Donan and Miss Delen, they will use that for some examples and problems.
Okay. Hello, good afternoon, everyone. Before anything else, allow me to introduce myself. I am Karen K. Dunan, one of the reporters for today's video. Okay, so now I was given the chance to explain further the topic that was being discussed by Ms. Katleya Jean Arobo. Okay, the independent trials. So, let's begin. So, again, as what was discussed earlier, independent trials, or should we say independent events, refers to those different events in which its results were not affected by the first or the other events. Okay, so for us to really appreciate what is meant when we say independent events, so we have provided sample problems for us to solve. Okay, but before we go through that, let us first talk about the formula of solving this particular topic. Okay, as you can see, the formula of solving the probability of independent events is this. The probability of A and B is equal to the probability of A, which is the first event, multiplied by the probability of B, which is the second event. Okay, take note guys take note that in this formula, we only have two events. Okay, however, there are problems which consist of two or more events. So, that's why the formula could be the probability of A, B, C, D, and so on. So, depende sa problem. Basta, there are instances nga mas daghan og events. Okay? So, I hope that this were now clear to you so that when we have our following problems and solutions, all of us can follow. Okay, so let's move on to our first example. Okay, suppose that you were asked to find the probability of tossing a head when you flip a coin, then choosing an ace from a standard deck of cards. How would you do it? Okay, so anyway, if you can notice guys, our problems is paulit-ulit, our situations is paulit-ulit, diba? Common na kayo ang flipping a coin, rolling a dice, or whatsoever, right? But then, I believe na this will help us to easily identify the difference between the previous topic that we have discussed. Okay? Kasi pag we have the same situations, we can easily identify the difference of how it will going to be solved. Okay? So, and with that, ganun din yung sample event natin for today's video. Okay? As we can see in this problem, we have two events, right? There are two events that is obviously belongs to independent events. Why? Because since the two events won't affect each other. Kasi nga, yung isa gumagamit ng coin and then the other use cards. Now, using the formula that we have, so we have to substitute. So, we are now have the probability of head and the probability of head and ace is equal to the probability of head multiplied by the probability of ace. Okay, so first we have to find the probability of head in tossing a coin and the probability of ace from a standard cards. So I believe kasi nga this situation, so this sample was already discussed by the previous reporters. I know na nakabalo na mo ani tanan. So, probability of head is equal to 1/2. And the probability of ace is equal to 4 over 52, or in a simplest form, 1/13. In a simplest form. So, 1/13 siya. Okay, so, we have the probability of head is 1/2 kasi nga may two sides yung coin. And then sa ace naman is mayroong 52 cards, yung standard cards, tapos may 4 ace. That's why 4 over 52. So, hindi ko na ilalaliman yung pagdidiscuss dyan kasi na-discuss na yan noon. So, since we already have the value that we need, we can now solve the probability of these two independent events. Okay? So, now we have the probability of head and ace is equal to 1/2 kasi yun yung value ng probability of head multiplied by 1 over 13 the value of the probability of ace. So, the answer is probability of head and ace is equal to 1 over 26. So, that's it. So, your answer can also be presented in a decimal or a percentage form. Okay, another example. A card is chosen at random from a deck of 52 cards. So it is then replaced and a second card is chosen. What is probability of choosing a jack or 8? So in this problem, we have the with replacement. Okay, so na-replace yung na-chose na card and then the second card is chosen. So the question is, what is the probability of choosing a jack or 8? So with the use of our formula, we have the probability of jack and 8 is equal to the probability of jack multiplied by the probability of 8. So upon solving the probability of 8 and the probability of jack, we come up to this value. So the probability of jack and 8 is equal to 1 over 13 times multiplied by 1 over 13. Okay. Kasi nga, sa standard cards, merong 52, diba, tayo na cards. Tapos, merong 4 na jack doon. So, that's why 4 over 52. Or in a simplest form, 1 over 13. So, ganun din sa 8. Kasi nga, may 52 cards, tapos may 4 na 8 doon. So, that's why 4 over 52 then. And in a simplest form, 1 over 13. So that's why our answer in this problem is the probability of jack and 8 is equal to 1 over 69. Okay, last example. Last example with this different situation na ha. Suppose a bag contains 30 candies with the following flavors. Okay, there are 10 strawberry, 10 oranges, 5 lemon, and 5 mango. So, calculate the probability of selecting mango, lemon, and orange candies in that order with replacement. Okay, with replacement daw ha, meaning, kapag may naselect ka, ibabalik mo, tapos mag-select ka na naman ng iba, na another. Okay, tapos ibabalik na naman. So, that is what is meant by with replacement. Okay, so when we say with replacement kasi, the sample space would not change, would not be affected. Therefore, it is an independent event. Okay, so now using the formula, we have the same formula. We will use the same formula, the probability of mango, lemon, and orange. So it will be multiplied by each other. Okay, so in getting the probability of mango, lemon, and orange separately, so we have, diba, we have 30 candies. Tapos, out of the 30 candies, we have 5 mango. So that's why 5 over 30. The same is true in the lemon. So we have 30 candies and out of the 30, we have 5 lemon flavored. Okay, and the orange we have 30 candies and we have 10 oranges. Okay, so in the simplest form, we have the 1/6 and the 1/3. Okay, so that's why we have the probability of mango, lemon, and orange is equal to the probability of 1/6 times the probability of 1/6 times the probability of 1/3. Okay, so that's why the result is equal to 1/108, or in a decimal form, the probability of mango, lemon, and orange is equal to 0.009. Okay, so I hope na you've learned how to solve the probability of independent events with these simple examples. Anyway, Ms. Biana Kiesha H. Delen will give you more complicated examples for you to understand it much deeper. Remember lang yun na in solving these problems, it is important na you know how to identify independent events from those dependent events para it will be easy for you to decide what formula na to be used in solving. Okay, thank you very much. Thank you for listening. Again, I am Karen K. Dunan. And if you have questions, clarifications, violent reactions, do not hesitate to raise it up at the end of this video. Thank you and God bless.
Hello everyone, I'm Biana Kisha H. Dilin. So now you know what independent trial means. But to further understand, I will give you an example and solution because the theory of independent trials will become much more clear if you are able to solve a problem. For example, let's say that I toss a biased coin that comes up with heads with probability P, so it's going to come up tails with probability 1 minus P. And let's say that I toss it 10 times. First, we have to find what's the probability that H for the very first flip, then T for the tails, and then H, then TH, T, H, 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 and then finally is T. Notice that each of these outcomes corresponds to the outcome of a given sub-experiment, and specifically, this is the outcome for experiment 1, this is the outcome of experiment 2, 3, 4, and so on until experiment 10. So the first question, we need to find the probability of getting H, T, H, TH, TH, HHT, and this can be obtained as the probability of getting the heads on the first flip times the probability of getting tails on the second flip, the probability of getting heads on the third flip, probability of getting the tails on the fourth flip, probability of getting our heads on the fifth flip, probability of getting tails on the sixth flip, then the probability of getting heads on the seventh, eighth, ninth, and finally, probability of getting tails on the 10th flip. So the probability of getting heads in P times 1 minus P times P times 1 minus P times P times 1 minus P times P times P times P times 1 minus P, and if I were to perform this, I'll get 1 minus P to the 4th times to the 6th. So that's a probability of exactly this sequence. Now, notice that this exact sequence has 6 heads. The first question is, what is the probability that you get exactly 6 heads? In the preceding example, we found that probability of exactly one sequence that has 6 heads. Notice that's how 6 heads are placed in this sequence, but there are numerous other ways in which you can place 6 heads out of 10 flips. Specifically, the question then becomes how many sequences are there that have exactly 6 heads, which can be answered by asking a question to ourselves, and that's in how many ways can we place 6 heads in 10 flips. That's the logic there, guys, and that answer is 10 to 6. So there are 10 to 6 such sequences like the one above, each having probability equal to 1 minus P to the 4 times P to the 6, because there are 6 heads and 4 tails. So the probability of getting exactly 6 heads is going to be equal to the summation of those individual probabilities of then choosing 6 sequences. This means that if I were to add all of those probabilities to all of those 10 to 6 sequences, I get 10 to 6 times 1 minus p to the 4 times p to the 6. So I repeat, the probability of getting 6 heads is 10 to 6 times 1 minus p to the 4 times p to the 6, where 1 minus p to the 4 times p to the 6 in the probability of exactly one sequence that has 6 heads, but there are 10 to 6 such sequences that have exactly 6 heads, each having the same probability. So if you were to add those probabilities together, you get the total probability as to 10 to 6 times 1 minus p to the p times p to the 6. The second question is, what is the probability that you get no more than 3 heads? The probability of getting less than 3 heads can be obtained in multiple ways, and those are the probability of getting 0 heads, but the probability of getting 1 head plus the probability of getting 2 heads. Each of these independent trials will satisfy this condition of less than 3 heads. Now, the probability of exactly one sequence that has 0 heads will be 1 minus p to the 10th times p to the 0, because I have 0 heads and I have 10 tails, and there are 10 choose 0 such sequences that have exactly 0 heads. Similarly, for the probability of getting 1 head or a sequence that has exactly 1 head, particular sequence with exactly 1 head will have the probability of 1 minus p to the 9th times p, and there are 10 chosen ones that sequences. The probability of an exact sequence with exactly 2 heads is going to be p squared times 1 minus p to the 8th, but there are 10 choose 2 such sequences. So the total probability will be by adding all of those individual probabilities, and that will give you the probability of less than 3 heads. So that would be all on my part. I hope that you learned something. Thank you.
The introduction and concepts of decision theory. In statistics, decision theory is a set of quantitative methods for reaching optimal decisions. In general, such consequences are not known with certainty but expressed as a set of probabilistic outcomes. Each outcome is assigned a utility value based on the preferences of the decision maker. Statistical decision theory involves procedures for choosing optimal decisions in the face of uncertainty. In the simplest situation, a decision maker must choose the one best decision from a finite set of alternatives when there are 2 or more possible future events called the states of nature that might occur. The list of possible states of nature includes everything that can happen, and the states of nature are defined so that only one of the states will occur. The outcome resulting from the combination of a decision alternative and a particular state of nature is referred to as the payoff. Payoffs may be a positive or a negative outcome. Simply put, decision theory is an analysis of decision-making process. Next, the decision-making components. Decision alternatives. These are the options or choices open to any decision maker. Identification of possible alternatives is the starting point for all decision theory. The alternatives are independent, mutually exclusive, and collectively exhaustive. The states of nature. These are any condition in nature that can occur after a decision has been made. The conditions affect the outcomes of the decision in either a positive, neutral, or negative way. The decision maker does not control the states of nature. Payoffs. These are the rewards for any given decision alternative. Payoffs can range in size and in some instances may be a loss. There are also 3 main areas of the decision theory. They are prescriptive decision theory. This theory aims to provide recommendations on how to make the best decisions even in an uncertain decision-making environment. Second, descriptive decision theory. This theory seeks to describe how irrational or irrational agents make certain decisions. And the third one is the normative decision theory. It is based on a set of values. This theory provides direction for how decisions can be made. Of course, there are also four basic elements in decision theory: the acts, events, outcomes, and payoffs. Acts are the actions being considered by the agent. In the example, taking the raincoat or not. Events are occurrences taking place outside the control of the agent. Example, rain or lack thereof. Outcomes also are the result of the occurrence or lack of it of acts and events. Staying dry or not, being burdened by the raincoat or not. Payoffs are the values the decision maker is placing on the occurrences. For example, how much being free of the nuisance of carrying a raincoat is worth to one. The conditions and goals of decision theory. It helps businesses achieve one of the following goals when selecting among alternative course of action: maximize the return, maximize the loss, and minimize regret. Let's proceed to the conditions of decision theory. First condition is decision making under certainty. All alternatives and conditions surrounding each are known. Second condition is the decision making under risk. All alternatives and conditions surrounding each are associated with probability estimates. And the third one is the decision making under uncertainty. All alternatives and conditions surrounding each are not completely known or understood.
A pleasant afternoon, each and everyone. I am Eliza Marie C. Alonde, and I will be giving problem and solution for decision theory topic. So, for our problem, Miss Park Minyong is the owner of Bella Sailia, which is a boutique that sells fashionable and luxurious items on trend. So, she is deciding whether she manufacture the accessories needed for her limited edition dress or she would purchase it from other suppliers. So, the result for profit is dependent upon the demand for the product. So, the following payoff table shows the projected profit for the limited edition dress. The decision alternatives are to manufacture or purchase the accessories needed for the limited edition dress. So, as you can see on the slide, manufacture is highlighted by color yellow, while the purchase is highlighted by color pink. The following outcomes are low demand, which is highlighted by color green, the medium demand, which is highlighted by color blue, and the high demand, which is highlighted by color violet. So, if Miss Park Minyong were to manufacture the accessories needed to her limited edition dress when it is in low demand, the projected profit is lost by 20,000. If in medium demand, the projected profit is 40,000. And if in high demand, the project profit is 100,000. The requirement for this problem is to show the order of decision and outcomes using a decision tree. For the solution, we start off with decision node. If Bella Sailia decides to manufacture the accessories needed for the dress, then there are three following outcomes. If it is in low demand, the company is projected to lose 20,000. If it is in medium demand, the company is projected to profit 40,000. And lastly, if it is in high demand, the company is projected to profit 100,000. On the other hand, if Bella Sailia decides to purchase the accessories needed for the dress, there is also three following outcomes. If it is in low demand, the company is projected to profit 10,000. If it is in medium demand, the company is projected to profit 45,000. And lastly, if it is in high demand, the company is projected to profit 70,000. Recall that a square represents a decision node. So node 1 shows the decision either to manufacture or purchase the accessories needed for the dress. Nodes 2 and 3 shows the outcomes when there is a low demand, medium demand, and high demand. And now, let's proceed to the folding back of a decision tree. So for the continuation, suppose that the state of nature probabilities are: probability for low demand is 35%, probability for medium demand is 35%, and the probability for high demand is 30%, for a total of 100%. The requirement now is to calculate the expected payoff at each outcome node and identify the best decision alternative based on the expected payoff. Let's look at this decision tree to help us out. EMV stands for expected monetary value. So for calculating, the expected payoff is 35% times negative 20,000 for low demand plus 35% times 40,000 for medium demand plus 30% times 100,000 for high demand. For low demand, it is equals to negative 7,000. In medium demand, it is equals to 14,000. And in high demand, it is equals to 30,000. So negative 7,000 plus 14,000 plus 30,000 is equals to 37,000. This equals to an expected payoff of 37,000 if Bella Sailia decides to manufacture the accessories needed for the limited edition dress. Now, let's calculate the expected payoff if the company were to purchase the accessories needed. To calculate, the expected payoff is 35% times 10,000 for low demand plus 35% times 45,000 for medium demand plus 30% times 70,000 for high demand. For low demand, it is equals to 3,500. For medium demand, it is equals to 15,750, and for high demand, it is equals to 21,000. So 3,500 plus 15,750 plus 21,000 is equals to 40,250. This equals to an expected payoff of 40,250 if Bella Sailia decides to purchase the accessories needed for the limited edition dress. So when we are folding back the decision tree, we need to first look at the payoff of each outcomes. Then multiply it by the probability of each outcome, which will give us the expected payoff at each outcome node. So at this slide, you can see the expected payoff for manufacturing is 37,000, which is the node 2. And the expected payoff for purchasing is 40,250, which is the node 3. Now, we can make a decision based on the expected payoff at each outcome node. Since we would want to maximize the profit, the best decision would be the outcome with the largest expected payoff. Therefore, the best decision alternative would be to purchase the accessories needed for the limited edition dress since it yields the largest amount of expected payoff of 40,250. That's it for my part. Let's proceed to the next reporter.
Good day, I am Shandy May M. Dimisilio, and at this moment, I will be giving an example with solution in regards with decision making. But in this example, we will be using decision tree to derive with the best possible decision. First, let's define what is decision tree. A decision tree can be used instead of a table to show alternatives, outcomes, and payoffs. Trees are much more powerful than tables, which are limited to 2 dimensions only. A decision tree consists of nodes and arcs. Square represents a decision node, circle represents outcome node, and arcs or lines indicates decision alternatives or outcomes. To apply this, let's have an example. Zephany is considering the possibility of starting a company to produce small sailboats. With a favorable market, Zephany expects to make 90,000 pesos from a large facility or 60,000 pesos from a smaller facility. If the market is unfavorable, Zephany estimates that she would lose 30,000 pesos with a large facility or 20,000 pesos with a small facility. She can also decide not to pursue her business idea. She estimates the probability of a successful market is 60%. Now, let's determine the decision node. Here we have three decision alternatives. It is either Zephany will start a company with a large or small facility or just not do it at all. Next, we have the three circles which represents the outcomes. The estimated success rate is 60%, that's why we have 0.6 for the favorable and 0.4 in the unfavorable. If Zephany will build a large facility, she expects to make 90,000 pesos with a favorable market and she would lose 30,000 pesos if the market is unfavorable. It is negative since it is a loss. For the second alternative, which is for small facility, she will get 60,000 pesos and a loss of 20,000 pesos if the market is unfavorable. For the last alternative, it simply means zero because she will not start her business idea. So basically, she gets zero income. The decision tree has now been developed, so we can start the process of identifying the optimal decision. Moving from right to left, let's calculate the expected payoff of each outcome node. The expected payoff of the first decision alternative, which is for the large facility, is 42,000 pesos. To get the expected payoff, let's simply multiply 90,000 to the estimated success rate, which is 0.6, and do the same to the unfavorable. However, it will be multiplied by 0.4, then add their product. So now we have the expected payoff of 42,000 pesos. That will be the estimated amount that Zephany will get if she chooses to have a large facility for her business. Then for the next alternative, let's just do what we did earlier. We come up by 28,000 pesos by multiplying 60,000 to 0.6, then multiply as well the negative 20,000 to 0.4, and then other product. So that's how we get 28,000. Lastly, it is zero. As what I said earlier, Zephany will get zero expected payoff if she decides not to continue her business idea. Before choosing the best possible decision, we need to identify the problem first in order to select the best decision alternative based on expected payoff at each outcome node. If it is for maximization problem, choose the largest payoff, and for the minimization problem, choose the lowest cost. And now, let's continue. Here, we have the expected monetary value for node 2, which is 42,000 pesos. For node 3, we have 28,000 pesos, and for node 4, we have 0. Since this problem is to identify which decision gives her more returns, so it is a maximization problem. Let's choose the largest payoff, which is 42,000 pesos. So, in order to have a payoff amounting to 42,000 pesos, Zephany should start a company using a large facility to produce the sailboats. And that concludes for the group report of Group 4. Thank you for listening and God bless us all.